All right, so in this video, we're now going to talk about double integrals over general regions. In the last video, we talked about rectangular regions, and if you'll remember, all of the bounds on the integrals were constants, and that's, again, because you were over a rectangular region. The only time there'll be constants everywhere is when you're over a rectangular region. When it's over a more general region, we're going to have to take the functions themselves into consideration. So there's going to be two different approaches we want to talk about here. We'll start by talking about approaching this vertically, and the vertically versus horizontally will make sense once you see the picture. And so let's suppose now we don't have a rectangular region anymore, but instead we have a region that looks something like this. Maybe one will look like that, maybe the other will look like this. And we're going to be studying now from x equals a to x equals b. And remember, this is the region in R2 that the rectangular prisms are going to be coming out of. Up above this, the z-axis comes out at you. Up above this, we have some surface. Underneath that surface, and then with the base of this region, we're going to have a volume. So that's what we're trying to compute. Let's not lose sight of the big picture here. Now, when it comes to labeling these things, I'm going to keep it pretty simple, much like I tried to do in, excuse me, in Calc 1, where I'm going to call this top function here, let's say y equals t for the top. So this top function here would be y equals t. This bottom function here would be y equals b for bottom. Now, to get this volume integral set up, I'm going to now say that I need a double integral under the surface, and then we have our dA sitting here. But if you remember, dA is some combination of dx dy or dy dx. For this particular setup vertically, I'm going to go ahead and sketch in a vertical bar right here. This vertical bar is going to run from A all the way over, scanning all the way over to B. And so by noting that it's going to start at A and end with B, that's going to push us in the direction of dy dx. Now, that might not be incredibly obvious right now, but I want you to think about this. If we go ahead and we integrate first with respect to y, that means we're going to integrate second with respect to x, which means the bounds on x are going to be a and b. So by me putting an a and a b right here, remember those are constants. The last integral that we compute and then evaluate at constants will give us a numerical value. When it comes to integrating with respect to y, this is where we're going to need our top function and our bottom function defined. So I would have a y equals t on top and a y equals b on bottom. I'll even put the y's in there. It's not a bad idea. So when you integrate with respect to y and then you evaluate, you're going to be actually plugging in functions for y. Then you'll integrate again with respect to x, finally evaluating at constants, getting that numerical volume. Okay, I know that's kind of a lot to take in on the video, but I think once you look at a few examples, it's going to make pretty good sense. The alternative here would be horizontally. And as I've pointed out, many times you're going to have options, and that's a good thing. And so let's suppose these are our functions. Let's suppose then that now we need to mark things as y equals c and y equals d. This we would call now maybe x equals the right and x equals the left. So this guy right here, the straight horizontal line would be y equals d, y equals c. This curve would be x equals the left, and this curve would be x equals the right. When we get this one set up, once again, double integral over surface f of xy, or under surface f of xy. And then we would need to pick our order. Much like the last one, I would say that dx dy is going to be the way to go, because finishing with y means we're finishing with constants C and D. So that'll be a C and a D. And then in terms of horizontally, I'll go ahead and sketch in my horizontal scanner. That scanner is going to sweep from top to bottom along this. And much like Calc 1, even when we talked about volumes or revolution for that matter, we've got a right and a left. We'll put the right on top and the left on bottom. So x equals the right on top, x equals the left on bottom. So these would be your two setups. If you have an option, one might work better than the other. You can certainly decide. But these are the two options moving forward now to find the volume over these general regions, which are no longer rectangles. All right, so we'll take a look at an example here where we're going to be finding the volume under this surface above region R. And region R is going to be bounded now by the two curves shown here on the screen. And so let me go ahead and set this up. We'll do it two ways. We're going to do it vertically, and we'll start with that, and then we'll go to horizontally. So in R2, and you'll notice all of the pictures that we draw are going to be basically in R2. I'm going to go ahead and sketch these curves right here. So the square root function will look something like this. That's going to be y equals the square root of x. And then that cube function is going to look something like this, where we have y equals x cubed. And so keep in mind that the surface, the z-axis is coming out at you. The surface is up here. We're looking to find the volume under this surface above and bounded by this region right here. Okay, so this is where the rectangular prisms are starting and coming out of up into the surface itself. So when we take a look at this, vertically, of course, I'm going to go ahead and put the vertical line in there. I'll do that in red. So here's our vertical line. So if you'll remember, the volume now is going to be the double integral. We'll put the function xy squared in there. And then being vertical, that's going to be a dy dx. We want to stop. We want our constants to be x equals. And so to figure this out, we could see pretty clearly that x is going to equal 0 right here. And then by taking the two functions and setting them equal to one another, so by taking this guy, setting it equal to this guy, which you've probably done 100 times in Calc 1 already, you would find out that in fact this equals 1. And so again, I took the square root of x and set it equal to x cubed. When I solve that, I get x equals 0 and I get x equals 1. You can certainly do that on your own if you need to. But regardless, that means that we're going to have a 0 here and a 1 here. Remember, you always want constants at the last integral because you want your answer to be a constant. Now, these are going to be the functions. And we talked about the top and the bottom. So the top is going to be this guy right here. That's going to be y equals the square root of x. So I'll put a square root of x right there. And then I'll have a bottom right here, which would be the x cubed. Now, one of the other things that I like to point out, and I've done this a little bit already, is especially for this first integral here, remember this is a y. So it's going to have to be y equals these things. And it's not a bad idea to get in that habit of including the y equals or the x equals depending on the direction, just to remind yourself again and don't get confused between what's a variable and what's a constant. So that's going to be the setup vertically. We'll come back and work this here in a second, but let's talk about it horizontally now. So the picture really doesn't change a whole lot. The picture is still going to look something like this, and it's still going to look like that. But now, as we draw these things in here horizontally, we're going to need to remember that the integral itself is going to be dx dy. So we're going to need y constants over here and x functions over here. So what you'll want to do is you'll want to come up here and solve each of these for x. This would give us an y to the second equals x for that guy, and this would give us y to the 1/3 equals x for that. So this guy right here, which was originally that, is now going to be x equals y squared, And then this guy here, which was originally that, is going to be x equals y to the 1/3. So x equals y to the 1/3. Additionally, those constants that I mentioned are going to be with respect to y are going to come here, which is clearly 0, and the other one would be about right here. To find those, you would want to set the y to the 1/3 equal to the y squared. You've probably done this one a bunch already as well. Once again, you would find out y equals 0 and y equals 1. So just a little bit of algebra there in solving that, much like you did up here. So then, when plugging it all in, the 0 and the 1, and that 0 and that 1 that I'm talking about there would be this 0 and this 1 right here. And then in terms of the x, it's going to be the right, then the left. So the right would be this guy, which is y to the 1/3. So I'm going to write x equals y to the 1/3. And then the left would be x equals y squared on this one. So there's the x equals y squared. And so there's your setup. Now, in this particular one, it doesn't really matter how you move forward. I don't know that one's necessarily better than the other, but I am going to, for practice, go ahead and work this one out with you guys so that you can better see how it's going to work now that you have functions in there. So to do this, I'll tell you what, I'm going to go ahead and clear the screen. I'll copy that down again, and then we'll just work it from scratch just for the practice. Okay, so now that I've got it copied down again, we'll go ahead and work this. You'll also notice that I went ahead and not only did I use a different color here just to make things a little more obvious, but I did put the y equals and the x equals there just to keep things very, very clear. So when we go ahead and integrate now, we'll say 0 and 1 there. We're integrating with respect to y first, with respect to y. So that's going to be a constant. Therefore, I'm going to end up with a 1/3 xy cubed. Evaluating this from y equals x cubed to y equals the square root of x dx. So every place I see a y, I'm going to plug in this guy to start, and then minus this guy gets plugged in after that. So that's going to be 1/3 x times x to the 3/2, and then minus 1/3 x to the 9th dx. So when that gets plugged in, that's going to give us the x to the 2/3. When that gets plugged in, that's going to give us the x to the 9th. Let me clean this up just a little bit. That'll be a 1/3 x to the 5/2 minus 1/3 x to the 10th. Now we're still adding 1 and dividing. So when I add 1 to this, I get 7/2. When I divide that, and with that 1/3 out in front, it's going to give me a 2/21 x to the 7/2, and then minus 1/33 when I divide by that 11, evaluating from 0 to 1. So 2/21 minus 1/33 is going to give us a final answer of 5/77. So again, nothing is different from previous problems we've worked, except now you're plugging in these functions instead of just constants like you did in the last section. So the last thing I'll say is even though we worked out the dy dx one, if you would have worked out the dx dy, you would have gotten the same answer. A lot of it depends, as I mentioned before, on how easy it is to integrate with respect to a certain variable, and that'll push your decision which way to go.